Hi everyone. Today we are going to start to filter design and statistical analysis in Python programming language. Okay, by using some basic libraries which is given in the Python program. Okay. So our topic is that the noise reduction in signal processing. Okay. And so in the real world application, for example, enhancing the audio clarity in telecommunication or the processing the biomedical signal can be useful for the for using the noise reduction in signal processing. Okay, because in mechatronic engineering perspective, we have some signal or the measurements taken from the system or devices. For example, if you are using the temperature or the pressure sensor, this sensor generates the noise in order to internal characteristics and the electronical part of your system. Okay, and so if we take these measurements without a noise, and then we will proceed either two ways, which is the former is the designing the real electronic filter by using the resistor or capacitor, but we don't have any chance to apply this case in every situations. Okay, and so we need to design some mathematical filters in order to remove your noisy signal from your main signal. Okay, and so enhancing audio clarity in telecommunications or removing unwanted noises from your measurements using the water pressure or any other transducer or the sensors from your system, but in using mathematical operations. Okay, so our method is simple. We need to design a filter out noise from a synthesized signal. Okay, and we need to design and apply a Butterworth filter, especially for the low pass filter, using cgpi.signal. Okay, cgpi.signal is used to build this kind of systems. Okay, for example, if we want to use the low pass filter or design the low pass filter or the high pass filter, we need to use this library, because this library contains some pre-trained or prepared functions in order to build this kind of filter. You don't know anything about the Butterworth filter, but you may search the internet in order to gain some information about it. Okay, in mechatronic application, we generally use the low pass or high pass filter or the band pass filter by using some additional mathematical tools. But in this case, we have huge advantage of achieving a balance between simplicity and effective noise reduction. Okay, in Python programming language, we may utilize these terms in order to with respect to your application it's given in the specific case. So in order to build our example, we need to add the numpy and import matplotlib.pyplot as plt in order to visualize our results in here, and also we need to add the cgpi.signal, import the butter filter and field function. Okay, I will explain the field and butter filter function. Firstly, we should give or generate the synthesized data or synthetic data in here. T is equal to the MP linspace 0, 1 and 200 variable. And signal can be built with the mp dot sinus 2 times mp pi times 5 hertz times t plus mp random dot normal distribution can be used in here 0, 0.5, which means that we have the mean values at the 0 value, and we have the 0.5 value at the standard deviation, and t shape can be given in here in order to generate the 200 data in here. Okay, and so how can we create the R filter design? B and A specific coefficients. You don't know anything about the B and A, but it's the simple coefficients in order to what? In order to multiplication of the R signal to remove the noises in here. Okay, and so the butter filter can be assigned with the N2. This is the this is the order of the R filter. Okay, just like the square form, x square plus x plus 1. Okay, and so if you take this term is equals to the 3 or 4, and then we will have the fourth order filter design. Okay, and Vn is also another parameter in here 0.1, because we need to give the some specific frequency in order to remove the noises. Okay, and so this Vn directly related to the selected frequency. For example, if you have selected the 50 Hertz frequency, we should assign the 0.1 in here, and which means that this generate the signal or remove the whole signal upper from the 50 Hertz signal. Okay, this is low pass filter. And filtered signal can be created with the field function. This is a standard convolutional operation to proper B and A and signal arguments. Okay, and so this signal is given to the field, and B and A creates the sum function to multiply with this signal, and this signals or the generated signal returns to the filtered signal in here. Okay, and PLT figure can be built in the fig size 6.4 PLT plot T signal label, which is equal to the noisy signal. Okay, it's the raw signal, and also we need to give the filtered signal in here. Okay, filtered signal, and it can be assigned in the form of the color in red. Okay, and PLT X label can be built with the time, and this is the amplitude values of this term, like this one, and PLT title noisy and filtered signal. Okay, and PLT legend should also be given in here, and PLT show must be given in here. Okay, and so if I run this code, and then we will have the two kind of signal in here, which is given in the in these terms. For example, the blue signal is the noisy signal, and then if we apply the filtered operation, which is designed with the low pass filter, and then we will have the some unnoisy or unwanted signal is removed from the main signal or the filtered signal, which is in the case of the R in here. Okay, and so we can filter the whole signal by using this operation. And so what's the importance of this method? In real world application, we have always noise signal. For example, if we measure the water pressure from the system using the water pressure transducer or the sensors, and then we will have this kind of blue line or blue signal, which is given in here. Okay, and so we want to design the electronical components by using the capacitor or the op-amp or the resistor values, but we don't need to change the every time to this electronical component. And so how can we update, or how can we apply the easily and flexible filter to be applied on this signal, and so we can create the mathematical filters, which is given in the what? The butter filter. Chebyshev filter or the some IRR or the FIR filter can be used in this case, and so you can generate the some another properties related to what the CGPy signal library, which contains what the low pass filter, high pass filter, IRR filter, FIR filter, or the something like that. Okay, you can use these filters to what? To remove your measurements. Okay, or the noisy measurements. This is the first example of the about the filtering signal. And so what about the frequency domain analysis? What is it? And so we need to import the numpy as MP, and we need to import matplotlib.pyplot as plt, and from cgpy.signal import butter field and frec z. Okay, this used to what? The frequency domain analysis in the what? In Python programming language. We always have the frequency components in our signals. For example, if we have the sinus signal in here, like this one with the 5 Hz, it's given in here, and then we may have the random normal distribution as a noise signal, but this noise signal is also contains the what? Our frequency components. For example, this includes the what? 100 Hz signal or 1000 Hz signal with a small amplitude. And so how can we discriminate for a given signal to what? To frequency components using the what? The Python library, which is given in the CGPy signal. And so firstly we need to generate the what? Generate two signals in here. T is equal to the MP linspace 0, 1, 200. Okay, and signal 1 can be created MP sinus 2 times MP pi times 5 times t plus MP random dot normal function. Okay, 0, 0.5 and t shape can be given in here, and signal 2 is also defined with the what? For example 12. Okay, and so this signal 1 is indicating to what? A sinus signal with the 5 Hz deviation, but the other one is equals to what? 12 Hz. Okay, and so we need to create the what? The butterworth filters, like B low and A low can be assigned with what? The butter, and n is degree is 2, we n is equal to 0, 1, and B type is equal to what? The low pass filter. Okay, and we can also define the B high, B A high, and butter n is equal to 2, and we n is equal to 0.3, and B type is equal to what? The high pass filter. Okay, and so we can create the band pass filter. We remove the noisy parts of the high frequency, and we remove the noisy parts of the low frequency by using these terms. Okay, and so how can we apply this filter? Firstly, we can generate the filter signal 1 is equal to field B low, A low, and signal 1, and signal 2 can also be defined with the what? The B high, A high, and signal 2. Okay, so how can we compare this, or how can we generate the frequency response of this signal? Firstly, frequency response of this term V low and high low is assigned fracs B low, A low, and worn 8 okay, 8,000, and V high and born, the number of the samples is assigned to 8,000. Okay, and so this returns to the what our filter characteristics under the circumstances that the frequency is applied to these signals. And so how come this filter responses the whole filter type or the frequency type upon its characteristics. Okay, and so we can use the Seaborn library for the plot setting. PLT style use Seaborn dark grid. Okay, and we should also contain the if Seaborn dark grid in PLT style available, else we need to use the PLT style dot use to what, to normal definition GG plot. Okay, GG plot. This is the standard definition of the what, the matplotlib library. Okay, you can easily check this condition if the what, if Seaborn is installed or not in your code. Okay, so time domain plot for signal 1 can be built with what, these terms, but firstly we need to give the figure fixed size, it's equal to 12.8. Okay, and PLT subplot 2 to 1 PLT dot plot T signal 1 label original signal 1 and color is blue and line style is equal to what, this term. Okay, and also be filtered signal 1 and low pass filtered signal. Okay, this is equal to what, the another term, but the line style is not given and dark orange can be given in here. PLTX label should also be given in here, time S, and PLT Y label amplitude can be given in here. Okay, and PLT title should be assigned. I'm sorry, PLT title signal 1 time domain PLT legend should be given in here. Okay, so same procedure for time domain plot for signal 2 can also be given in here, subplot 222. Okay, and PLT plot T signal 2, the label is original signal 2. Okay, and color is equals to green and line style is equal to comma. Okay, and plot T filtered signal 2 label high pass filtered color red. Okay, PLT X label time, second y label, amplitude, and PLT title, signal to time domain. Okay. After that, we should give the frequency response of these signals. Frequency responses for low pass filter. PLT subplot 223 PLT plot 0.5 times V low values divided by MP pi, because 2 times P times frequency creates the natural frequency or the angular frequency of this component, and then we can reverse the whole operation in order to build our frequency range. For example, 1 Hz, 2 Hz, 3 Hz, blah blah blah. Okay. MP abstract values, absolute values, H low, and color blue. Okay. And so we need to give the PLT title low pass filter frequency responses. Okay. And PLT X label normalized frequency in here, like this one, and PLT Y label, it's a gain. Okay. At every filter design we have the gain. For example, if we have the gain which is equal to the 1, which means that we pass the whole signal at the same way. But if we have this gain, for example 0.1, and so which means that this filter does not respond this frequency or the signal, because this signal is the higher frequency, has the higher frequency, for example 100 or 1000 or 10,000 frequency, which is the way of the generation or the building the filter design in math. Okay. And also we should give the frequency responses for high pass filter. Okay. PLT subplot 224 PLT dot plot 0.5 times V high divided by MP pi, MP absolute values of the hash high. Okay. And color must be used in green. We should use the absolute value because we have the real and imaginary part of this filter. Okay. And PLT title high pass filter frequency responses. Okay. PLT X label, which is the normalized frequency, and PLT Y label, which is the gain. Okay. So PLT tight layout should be given in here, and PLT show must be given in here. Okay. If I run this code, and then we will have the 4 plots in here. For example, I'm sorry, time domain here, PLT legend should also be given here. Okay. So in this filter, firstly we should look at the signal 1 time domain frequency. Okay. And so we have the filtered signal like this one, and so we have the low pass filter frequency characteristics, which means that this is the normalized frequency. Normalized frequency means that we have the sampling rate or sampling frequency. For example, if it's equal to the 500 Hertz, and so this normalized frequency is the equals to 500 Hertz. Okay. And so this 500 Hertz divided by 2, which is equal to the up to 1 frequency, and so which means that 250 Hertz represents the in the normalized frequency as equals to the 1. Okay. But just remember that this is the signal of the high gain range, which means that we have the components of these terms in here, like this one up to now. Okay, for example, if we have the signal in here, plot IP, so for example, if we have the sampling frequency range, can be defined in here. Okay, there are 500s, and this sampling frequency should be divided by 2, okay, at each case, because the Nyquist criteria should give us. Okay, this is more useful or observable in this case. Okay, so we need to understand that this gain is equal to 1. Okay, and so which means that we have at here, or the up to 20 hertz, we pass the signal with the gain of the up to 0.4. okay, but in this case up to 5 hertz we completely transfer the signal to the another one, or the low pass filter formation. Okay, but in the highest frequency we don't have any characteristics in here, because this gain is so small, which means that this gain is smaller and smaller than the 1, and then this highly frequency components, or the noisy signals, is removed from the filtered signals. This is the low pass case. But in the high pass filter frequency characteristics, we have the original signal like this one. Okay, but we don't have the main parts of this signal, just only the removed or the noisy signal is given here, because at the 60 hertz we have reaching to the gain is equal to the 1, which means that we transfer the whole noisy signal to the another part, just like that. But for example, if I have these formulations in here like this one, which is the design of these terms in here, and so if I select the Vn is equal to 0.5, and so which means that we increase the high pass frequency range, and so this range is going to the 100 in here, but in the previous case we have the 60 hertz, and so we increase this signal, and so this noisy parts is increased in here like this one, because this only contains the contaminated or the unmuted signals is in here. Or in this low pass filter characteristics we have the smallest values of this signal, up to 5 hertz is passed using this filter. But if I choose increase the 0.2 in here, and so the low pass filter generates to unconditional or some noisy signals in here. For example, the dark orange signals contains now the some unwanted signals in here, but in the smallest way, smaller ratio. Okay, just see that. If I choose the 0.4, or which means that we have the high branch for the low pass region, and so just see that this dark orange signal is equals to the is equals to the another one. Okay, so this must be represented with the red line in here, red. Okay, okay, and so we don't have any filtering operation in here, but we have this for example 0.2 time at this seconds, and so we bypass some unwanted noises, but the whole characteristics is is preserved in here. But if I choose the lowest values of these terms, for example 0.05, what happens in our signal? And so we have the smooth signal in here, but we have this ratio or this pattern is smaller than the previous one, which means that we may have some loss important features from this signal. And so in order to select the best frequency for the low pass and high pass is an optimization problem. Okay, this selection should be optimized for your system design. Okay, just remember that. Okay, this is the first example of these terms, and in the next session we will talk about the statistical analysis and the numerical integration in the what in the system design. Okay, let's take a 10 minutes break and then we will continue these filter types. Okay.